Yeah, so this collaboration between me and Owen and Pierre Alexandre from University of Huddersfield and Anna from Queen Mary University. So I'm going to present a little library for visualization of audio descriptors. This is a work that emerged from a research project we are in at Huddersfield called FluComa, about fluid corpus manipulation. So we're interested in using large or moderately large databases of sounds for creative applications, mainly for music creation. And in this context, we thought we'd be interested in exploring how this user interface for that would look like. And first step would be how to represent sounds. So in the longer term, we're interested in representing the collection of sounds. But in this work, we only look at how to represent each sound. And we thought a good tool for this would be the large amount of audio descriptors that have been developed in audio and music information research in the last few years. And these descriptors can be obtained automatically so that we don't have to actually know what's in the audio. So these kind of descriptors, they've been mainly popularized by speech recognition and music information retrieval, and they are fed to machine learning algorithms, although current trends in machine learning are more like about learning the descriptors automatically. But there's a long history of research that has produced hand-engineered features that kind of try to represent perceptual aspects or music concepts that are there, and they could be useful for visualization. And we feel that this is a bit of a potential that is not been developed enough. Some problems some possible reasons why this hasn't happened is some of the descriptors are not very intuitive, but maybe some of them are, and some just need a bit of more processing. Some are not intuitive because they're nonsensical when they're not used in the appropriate case. So, for example, a measure of pitch for a non-pitch sound would maybe a bit noisy, so you have to make sure you know when the sound is pitched or not. The library that we're working on, so the context or the related work would be existing visualization tools such as Sonic Visualizer or eAnalysis. These are desktop applications that you can use for musicology, for example, in the case of eAnalysis. In the case of Sonic Visualizer, I think it's more useful for research. It can also be used for musicology for sure, but I guess it's more used for research in signal processing and music information retrieval. And then, so what we're trying to do is to take the things you can do with these programs and bring that to new applications in web audio. Sorry. So in terms of visualization on the web, the classic, I think one of the most well-known frameworks is D3. And D3 popularized the idea of using method chaining as a kind of domain-specific language that allows you to make quite complex visualizations. Then another example is data to music. This is a library for sonification, not for visualization. But it does include, it's quite similar to what we do in terms of processing a time series and then rendering it into another domain. And then probably the most similar framework to what we're doing is Wave.js, which is a more comprehensive library basically for application, for making applications, web audio applications. So it includes many different components that you can use. And our goal is much more focused in that we just try to actually draw descriptors and do the processing that we need to do that. So in this sense, Wave.js, I think like D3, by accepting the idea of using scalable vector graphics, this kind of leads you to a kind of more complicated relationship with the document object model. Whereas our approaches take the canvas as something that is kind of, it allows you to do something that is less opinionated in terms of the application. So instead of having more like rich abstractions and components for application building, we just focus on this task of drawing. And we also hope that this will have perhaps better performance for case of visualizing collections of sounds. And for example, for visualizing something like a spectrogram, which is basically a bitmap, it felt like the canvas is more the right tool for this. So so the design is quite simple. We don't do the feature extraction ourselves. We rely on third-party libraries or services. In the examples, we use JS extract, and so JS extract and media are the main, I think the most well-known feature extraction libraries for JavaScript. But you can use also like Essentia, I think, can be compiled for JavaScript, and you can use a web service to provide, for example, the FreeZone API can give you descriptors as well. And then what we do is we have this signal object that holds the sample rate, sorry for the typo, and they can be one-dimensional, two-dimensional, and then it has a virtual type. They're all float32 arrays, but they have kind of a virtual type tag. And then you chain operations on those, and you finally render on a display object. So the types of operations that we have unary operators that basically take one signal and return another signal. So you can slice it, scale, smooth, threshold, normalize. There are quite a number of them. Perhaps the most important one is resample, because obviously we need to resample the signal to fit into display. So it's not audio resampling, it's more like a kind of visualization style of resampling where we partition the data in buckets, and for each bucket we take a statistic like a mean or a standard deviation or the minimum and the maximum, and then we use that for rendering. And then another feature is we can combine several descriptors. So for example, in the case where I mentioned, if you have a signal that has pitch only at certain regions, and you have a signal that tells you the confidence on the fact that the signal is pitched, so pitch confidence descriptor, you can use the pitch confidence to threshold and to only show the pitch when there is pitch. But we can do all sorts of combinations of features to render kind of more interesting visual aspects. Then the displays are basically, they are attached to a container, to a div in the DOM, and then they hold multiple layers that are superimposed. Each layer is attached to a canvas. And then we have different kinds of drawing functions. And we can also, for each drawing function, we can assign a style, a CSS style that applies to the canvas, or we can also modify different elements of hue, saturation, and lightness. And that I'll show you can be used for doing visual effects as well. So yeah, so I'll go with the examples. I think I'll finish pretty soon. So this is an example of rendering a spectrogram. So here when we write get signal, it's just a function that gets us a descriptor. So as I said, we're not doing that part. We rely on, in this case, JS extract. We're getting the spectrum, which is a two-dimensional signal, and the RMS, which is a one-dimensional signal. We create the display. The display, by default, creates one initial layer, which is of style image. And then the second layer, we tell it to style fill. And then we threshold the RMS, and therefore the binary signal that results from that creates these red rectangles that kind of highlight the nodes or the events in the spectrogram. So a second example is how to combine descriptors. So if you see, for example, in FreeZone, that's quite a classic way of displaying a waveform with a spectral centroid mapping to the color. So that's what we're doing here. We use the wave drawing function for drawing the waveform, but then in the second parameter we use the hue, saturation, lightness, in this case the hue, where we take the centroid and scale it to appropriate values for controlling the hue. And then another example is kind of doing the same thing, but with RMS and controlling the lightness, where you already see the amplitude in the waveform, but you can use this to kind of create a more aesthetic reinforcement of the decay. Then another example, sorry. Here we tried to make actually something useful instead of just visualization. So this was a bit of an exercise of combining several descriptors to try to actually do some more complicated segmentation. So normally this is a snare drum sound. Normally it is easy to get the onsets there are many descriptors for onsets. It is not so easy to get where's the offset of a note. So in this case, by playing with RMS and the derivative of the RMS and then thresholding it and then combining both, we got to do a segmentation that isolates one note from the onset and the offset. And finally, here's an example of a bit of more creative kind of visualization where one of our colleagues plays with cardboard sounds. It has a collection of cardboard sounds, and we want to explore how we could obtain kind of fingerprints of these sounds for identifying them, combining quite a few or 4 descriptors and using these kind of error bars to show the patterns of the descriptors over the sounds. And they're mostly very correlated, but you can see that they correlate differently for every sound, and they create a more I don't know, interesting visual representation of the sounds. To conclude, I think this is obviously a work in progress, and as any software project. But I think so far we're quite excited. I think it shows it shows some promise for the use of the descriptors to represent sounds in web audio applications. So far, the descriptors are perhaps a bit limited, the ones that we extracted from JS extract. So we hope to explore other sources of descriptors. And we also hope to improve and to actually check. We haven't really tested much for performance, but there's obviously some catching that you can do. Once you do all these transformations, you can store the transformations in the signal in the intermediate versions that you're using. And then we want to try on other environments like Mac. So in Mac you have a JavaScript that you can use for visualize as well, or doing desktop applications with Electron. And that's all. You can access the code in our GitHub project. And thank you very much. And I'm ready for questions.
All right. I don't see any questions yet up on the Slack channel. Not sure what that means. Should I? I'll ask a question really quick. Send me something, or I guess if anybody has one, I suppose we could raise our hand and we go from there. Just see someone's typing. It's good. They're coming up. I guess one question while we have it going. I was curious what kind of, I saw a couple different types of visualization. One was like onion skinning different informational layers. Another was actually changing the color and changing the shape of the waveform itself. And I was just curious if you had any other thoughts about what things were more effective, or if they were effective for specific uses or that kind of thing. Or you're just trying things out to see what you might get at the moment.
Yeah, we're mainly trying things out. I would be really interested in exploring the spectrogram, but not necessarily a full spectrogram, but perhaps spectrograms based on filter banks, kind of more with a smaller number of bands. But that depends a bit on performance. So I would say the idea of coloring the waveforms is quite interesting, and having several descriptors in one visualization. So we're interested in this kind of idea for visualizing a sound bank. So I mentioned D3, for example. I used D3 in the past to do the layout of the sounds in the plane, and then, depending on performance, as much information as we can put in one of the waveforms or spectrograms. I think that would be interesting.
And one of our questions actually follows that as well. They're asking, does this perform in real time?
Well, that's not really real time. So it's not thought for real-time visualization. It's more like for interactive applications. So we haven't really thought about real time at all.
And then while you're go ahead and switch in, there's one last question, and that was, what was the web link on the first slide, the WebSonify one?
I think that's from the previous.
That's
web-sonify.glitch.me.
web-sonify.glitch.me. Or come down here afterwards. Or if someone would just type that in, that'd be great. Cool. All right. Well, thank you very much.